Warmly welcome to the webinar of Marcus Wallenberg Prize. Today with the title Nano Cellulose, 10 Years of Success. Today we will hear about what has happened in the area of nanocellulose research and application development since the area was awarded 2 prizes in 2013 and 2015. I'm Mikael Hannus. I'm the Executive Secretary of the Marcus Wallenberg Foundation that is giving out the Marcus Wallenberg Prize. And please let me remind you about the purpose of the Marcus Wallenberg Prize. It is to recognize, encourage, and stimulate path-breaking scientific achievements which contribute significantly to broadening knowledge and technical development within the field of importance to forestry and forest industry. Additionally, today, after the end of the webinar, we will announce the 2025 winners of the Marcus Wallenberg Prize. But now back to the webinar itself. I would like to introduce the webinar host, Professor Lars Berglund from Royal Institute of Technology in Stockholm. Lars has an outstanding track record in material science research, including but not exclusively related to nanocellulose. It is a true honor for me to have a leading topic expert as our host. Most welcome, Professor Berglund. Please take it away.
Thank you, Mikael. So for the MWP webinar, we have a long list of most valuable players. We have a very good list of speakers. And the first speaker on nanocellulose is Professor Akira Isogai from the University of Tokyo. He's a previous winner of the MWP Prize, and he won the prize together with Saito and Nishiyama. And the basic idea was really to carry out oxidation of cellulose. And I think this was really an interest from Professor Isogai. And there's quite a lot of serendipity in resulting in this prize. And what happens when you carry out this is that you get very fine fibrils and of high quality, very well dispersed in water. And this type of fibers are very common in Japan. And I look forward to listen to the talk from Professor Isogai. Please.
Thank you for kind introduction. And it is my great pleasure to join this workshop. And I would like to briefly introduce what's going on in Japan about nanocellulose materials. As you can see, there are so many surface modification chemistry developed in Japan. The first purpose is to develop the new nanocellulose materials, because in Japan, the companies and the laboratories are so competitive. So they are trying to, even though we reported the fast tempo oxidation, but other companies are also trying to develop a new and most cost-effective, safe, or some advantageous materials. Eventually, the phosphorylation and the carboxymethylation is very conventional, but the key point is just keeping the crystalline cellulose microfiber structure just on the surface of the hydroxyl groups can be modified by, for example, the oxidation, phosphorylation, and the phosphide esterification, carbonylation, carboxymethylation, xanthate esterification, and such. Especially the carboxymethylation is very safe for foods. So many various food, but not so large amount, but carboxymethylation originally developed in Sweden, and also this cellulase treatment, most of the mechanically fibrillated cellulose production companies are using this technique. But other things are also very interesting. Most of them, the the key point is introducing this on the surface charged group, minus charged group, which can easily separate the individual cellulose microfiber with less mechanical forces or like this. And as you can see the next slide, so many companies and research laboratories have developed their own original CNF or mechanically fibrillated cellulose. Number one shows a chemically pretreated CNF or CNCs or MFCs. And the number two is just a mechanically disintegrated water. But I believe that most of them, they are using enzymatic pretreatment to reduce the fibrillation energy. But anyway, so many companies are producing the pilot plant scale or a large plant scale. Its capacity is 500 tons per year. But the real production quantity is, I think, totally less than 100 or 200 dry ton per year. So they are trying to increase the quantity and the quality of the CNC, CNF, and microfibrillated cellulose, and also the chemically modified fibers. I will explain later. And later, Mr. Matsunaga of NEDO. NEDO is abbreviation New Energy and Industrial Technology Development Organization from the Ministry of Economy, Trade in METI. They selected these 13 CNF-related research projects from 2020 to 2024, already finished, but I would like to ask Matsunaga-san of NEDO, how much percentage of their numerical target can be achieved by individual companies? Let's see, for example, this company. Our university, our laboratory is something like, let's see, how to say, the subcontractors, not major, but Kao company as a Nippon Paper, we supported from scientific aspects, and most of them are let's say composite. It's a large quantity, so it's a challenging, but if we can develop the large quantity of CNF containing composite, it will, help the Japanese economy and employment, or some, new bio-based economy will be established. Matsunaga-san will explain later. And this is one example. Kao company. Kao is a chemical company or a commodity company, has already released this CNF containing strong, beautiful, flexible, and ductile material trade name Lunar Flex. Luna is the moon of the Kao company's trademark. And also Lunar Flow is another one. It's a very, I'm not sure it's increasing in quantity, but not so large amount, but very good successful starting they have already. And I would like to introduce three companies characteristic nanocellulose. One is, of course, tempo catalyzed oxidation, structure of cellulose CONA, and prepared under these conditions, and the water aqueous condition for a short time by catalytic reaction. And mostly C6 carboxyl groups just on the surface of crystalline cellulose microfibers can be converted carboxylate groups, which resulted in the easily fibrillation in water by mild mechanical disintegration. But some side reaction cannot be avoided. And I heard that tempo is a toxic compound, and also bleach does not seem to be favorable in EU. So we have to now, the new catalytic reaction for cellulose. But anyway, the Nippon says is very serious. And OG developed their own method of phosphorylated system. Of course, phosphorylation itself is a very conventional reaction, but using the urea as a melted urea as a solvent, only crystalline cellulose fiber surface can be phosphorylated, introducing the minus charge abundantly, which can result in such a completely nanofibrillated compound. And another one is not charged group, but Dio company, Dio paper company is very serious about carbamylation. This is just heating with urea at over 150 degrees C. Water molecules are of course removed by evaporation, and the melted urea can form this carbamate structure sufficiently, and it's very good results of the composite with polypropylene and polyethylene to produce a master batch. I heard it's the new plant producing 2,000 ton per year for producing master batch. And I think without introducing charge group, it's also very keeping the high molecular weight, and just on the surface of the crystalline cellulose microfibers can be modified, chemically modified. And these are some example of the Tempo CNF application. See the super deodorant diapers, ballpoint pen, and clothes, spray, tire, and metal coating of Lexus, only Lexus, because it's expensive. And some application, golf shaft and that. But as you can see, the Tempo CNF is completely nanofibrillated, but the application phase is so high value, but very small amounts. That is it's a usual process to increase the CNF quantity, but we realize that the nano materials to let's say to make advantageous point of nano material nanomorphologies, the quantity, for example, the additional level ballpoint pen ink is very small amount, but good results are obtained. So let's say, for example, tempo oxidation, phosphorylation, carbamylation, but the end products of nano materials is not so large at this moment because of the price is so high and water content so large. Then we are focusing on rather than the nanomaterials, but also microfibrillated in Canada also looks like, and Sweden as well, microfibrillated or fibrous material, but it's not conventional paper pulps. It's abundant charged groups are present in there, which can be used as scaffold to attach the nanoparticle, cationic nanoparticle, cationic metal ions, and for catalyst or such and such, because these fiber and the MFC can be used, can be converted to sheets using conventional paper machine or coating machine, which has already installed as a infrastructures in many papers. The Japanese in Japan also the pulp and paper, especially the printing writing demand is shrinking, so they are trying to develop new, sheet-like materials. So such chemically modified new looks like same fiber morphology, but different chemical structure can be used as new resources for sheet-like functional materials. Okay, that's it. And this is a good season for cherry blossom, almost gone, but if you have a chance, you can come to Japan within 2-3 days. You can have a chance to see the cherry blossom. Thank you so much.
Thank you very much, Akira. So the second nanocellulose presentation will be given by Professor Emily Cranston. She's a visiting professor at KTH for the spring semester. Her permanent position is as a professor at the University of British Columbia in Vancouver, Canada. And I'm sorry, I have to digress, Emily. So Tuesday night, the ice hockey team Vancouver Canucks were losing 5-2 with 1 minute left. They scored 3 goals in 60 seconds and went on to win the game. I think that you're also a nanocellulose winner. Emily worked together with Derek Gray, who is also a winner of the MWP Prize, and she's the world authority on preparation of cellulose nanocrystals and characterization. And she's also done lots of interesting work on materials from cellulose nanocrystals. Please, Emily.
Thank you so much, Lars. Great. Well, thank you so much. It's a true honor to be here today to tell you about cellulose nanocrystal development in Canada. I'm from the University of British Columbia, which is on the very west coast of Canada, but I'm born on the east coast in Nova Scotia. And I have studied and worked in the center of Canada, in Quebec and Ontario, and so it really is a great privilege that I've been a part of nanocellulose development in Canada from coast to coast over the last 2 decades. Now, obviously, Canada is a huge country. We have a lot of forests, and we have a lot of diversity. And that diversity is also represented in the types of nanocellulose that we produce. And so I'd also like to say a special thank you to Professor Isogai for really kickstarting our discussion today and for setting the stage for cellulose nanofibrils and their production and applications in Japan. But now I'm going to switch gears to cellulose nanocrystals. So if we talk about that in pictures, we can say that we go from the tree to the pulp fibers, and then we normally say that there are 2 different kinds of nanocellulose, either the spaghetti-like cellulose nanofibrils or the rice-like cellulose nanocrystals. And so that's where I'm going to be focusing today. These are whiskers or needles of crystalline material that are made by chemical routes, either acid hydrolysis or oxidative methods. In fact, there's over 30 different good methods to get high-quality cellulose nanocrystals, and they can be made from at least 40 different starting biomass sources. And so what's really exciting here is that we can use different production routes as a way to tailor the performance of cellulose nanocrystals and therefore the applications that they're used in. For those that aren't familiar, cellulose nanocrystals are shown here on the slide and some of their key properties. So again, they're these whiskers or needle-shaped. They're highly crystalline, which means that within the nanoparticle, the polymer molecules are all packed and aligned. And this crystallinity makes them strong and stiff. It also makes us able to align them using external electric and magnetic fields. Now, for an organic, natural material, cellulose nanocrystals are incredibly stable. So they're chemically stable, they're thermally stable, and they're colloidally stable, by which I mean if we disperse them in water, we get individual nanoparticles that stay suspended and make the nice liquid-looking solution that you can see in the photo here. And so this stays like this over a long term, but if we want to concentrate it, we can get gels, or we can dry it by different methods to get fluffy white powders or dense white powders. And in fact, the understanding of drying and redispersion of cellulose nanocrystals has been an important new advance in the field in the last 10 years. And so what this means is that we can take the spray-dried powder, put it back in water, and get the original properties of the suspension back. And that's pretty unheard of. In fact, for most nanomaterials, when you dry them, they aggregate permanently. And so this is great. It means we don't have to ship water around the world anymore, and we also can avoid some of the complications with storing materials long-term in water. Now, the last thing is, if we take these suspensions of cellulose nanocrystals and we dry them down slowly, they self-assemble into liquid crystals. That means that the particles start to order and they form these interesting structures, but it remains a liquid. If we keep drying, we end up getting these iridescent dried films that have bright colors and have the structure locked into them. And so the color that we can get in these materials is really the same as the color we find in nature in things like butterflies and beetle shells. And it really gets around a lot of the issues with sustainability and toxicity of a lot of other dyes and pigments that are available. And so in fact, this discovery that cellulose nanocrystals could form these bright, beautiful colors and iridescent pigments is what the Marcus Wallenberg Prize was awarded to Derek Gray for in 2013. And over the last 10 years, a lot of researchers have continued to work in this area in order to advance the field and are working towards the production on an industrial scale with a number of spin-off companies as well. So if I had to pick my top 3 nano advantages of cellulose nanocrystals, I'd highlight the size and the shape and the high surface area, which really just means that you only need a tiny bit to greatly change the properties of the surrounding material. We can also say that cellulose nanocrystals are lightweight reinforcing agents, and they're ideal at stabilizing interfaces. So oil-water interfaces and water-air interfaces so that we can enhance foams and gels and emulsions. We can also use cellulose nanocrystals to disperse other nanomaterials that aren't dispersible in water to make them more easily processed in water. And so building on these key properties, there are a huge number of scientific advances that have come from Canadian researchers. Obviously, this slide doesn't show all of them. It's just a snapshot of some of the contributions. And again, I'll highlight Derek Gray's work at McGill, which was on this self-assembly and liquid crystals and the optical properties that we can get from cellulose nanocrystals, and for which the Marcus Wallenberg Prize was awarded in 2013. And so some other interesting advances have been things like looking at CNCs to template color in other materials, using them as hybrid or even chiral catalysts, using them in energy production and storage devices, in water purification, in sensors, in drug delivery, and then more recently in areas like antimicrobial surface coatings and latexes for adhesive and coating applications. Now, this huge increase in activity that's happened over the last 10 years has really been mirrored in the Canadian publications and patents that have come out in this area as well. And so the commercialization journey follows a similar path to the scientific contributions from Canada, where here I'm plotting commercial readiness on the y-axis and technology readiness on the x, but again, this same increase, really an exponential growth in what's happening for cellulose nanocrystals. So starting from the work at McGill and then moving on to the Pulp and Paper Research Institute of Canada, or FP Innovations, their work was absolutely crucial and led to CelluForce, which was a joint venture between FP Innovations and Domtar, and producing the world's first demonstration plant producing cellulose nanocrystals in ton per day capacities. And so that was a really important point along the commercialization journey, as well Schlumberger and Suzano becoming partners with CelluForce, and now we sit in this multi-sector, multi-producer commercialization zone. And a few other key points to point out along the way have been toxicity testing done as early as 2010, the fact that cellulose nanocrystals are listed as the first safe nanomaterial on the Canadian domestic substance listing, as well as ongoing regulatory and safety efforts. And so again, this real momentum, productivity has been recognized with awards, some of the biggest awards in Canada and internationally that have been awarded around nanocellulose. And so again, highlighting Derek Gray, but also here on this slide, Richard Berry and Wadud Hamad, Mike Cunningham and Theo van de Ven, and then my own Rutherford Medal in Chemistry. But again, all of this activity has really linked to a lot of interest, a lot of awareness, and momentum. That means we now have a lot of players on the production of nanocellulose in Canada. So again, from coast to coast, different kinds of nanocellulose being produced at different capacities, and a lot of this has really come out in the last 10 years. But since today I'm focusing on cellulose nanocrystals, I'll highlight again CelluForce, which remains the world's largest producer of cellulose nanocrystals with ton per day capacity. They produce sulfated CNCs using sulfuric acid hydrolysis. Now, following close behind, we have Anomera with 0.5 ton per day of a carboxylated cellulose nanocrystal made using hydrogen peroxide oxidation. And then the other players in CNCs here are Cellulose Lab, Blue Goose Biorefineries, and Innotech Alberta. And so we believe that different suppliers are important for market growth and that this is an important contribution over the last few years. And then other efforts have really focused around looking at the sustainability of the production processes. So looking at ways to lower the energy footprint, looking at being sure we're following the tenets of green chemistry, different ways to recycle the reagents or to add value to some of the side products. So there continues to be work in the production and the scale up of providing cellulose nanocrystals. Now, if we look at cellulose nanocrystal producers around the world, this is now listing all of the companies that make them. Again, you can see CelluForce and Anomera in Canada that come out at the top there. A few players that I haven't mentioned already are Grand Bio in the US, Melodia in Israel, Fibinol in Estonia, the USDA Forest Products Lab, and then one company that's not included on this list but I wanted to mention is An Poly, and they're in Korea and producing a number of different kinds of nanocellulose as well. So lots of people to watch out for and lots of really interesting materials. So where my research group fits in is really to bridge the gap between these industrial producers of nanocellulose and potential commercial receptors of new technology. And really what that means is that we're trying to come up with new science and technology and the ability to tailor nanocellulose properties for strategic industries. Or in other words, what it means we're trying to do is link properties to the performance so that we have design rules and, for example, end user's guide so that we can help people to choose the best kind of nanocellulose for a given application. And so one of our efforts to this end has been in looking at benchmarking commercial CNCs. And so taking the 9 CNCs that are produced commercially on an industrial scale and really looking at full characterization and trying to identify what are the key base properties and is further purification needed when you buy these materials. So across the board, the characterization looks really good. We have great, uniform, clean, reproducible materials, and the situation is really quite positive. And I think from doing this work, one of the results was that we can now sort of recommend the best kind of CNC for a given application. So if you want the most thermally stable, the best rheological control, the best optical performance, then we can tell you which one, and we know why based on the properties. And so that's been an important advancement both from a scientific perspective, but also for product development. And so when we talk about applications and products from cellulose nanocrystals, we normally talk about it in terms of application suites or categories, and some of them are listed here. But really, I think the most exciting thing is that the possibilities are really endless. And so I've had the great fortune to work in a number of these areas, but this is only some of them. And so in some cases, we're using cellulose nanocrystals to replace plastics or to displace petrochemical-based materials. In other applications, we're enhancing existing materials, or we're enabling entirely new technologies that haven't been around before. And so the other thing that stands out and makes CNCs really unique is that the main property of the CNCs that is being used in each of these applications is often different. So for example, if we want to play on the rheological properties, that's necessary for oil and gas applications. If we're using CNC's optical properties, that's great in paints and cosmetics. We can look at barrier properties in paper coatings. We can look at reinforcement in packaging, in composites, or even in porous absorbents. We can think about the water binding ability of cellulose nanocrystals, which is absolutely crucial for cement and concrete processing. And so this is just a few examples of the different properties that are being highlighted in different applications. And that is pretty unique for nanomaterials. Often one nanomaterial always brings the same property, but cellulose nanocrystals can do more. And so if we talk about actual commercial products that are on the market, this is the list of the products that I know about. So for example, we have cosmetics, using them as plastic microbead replacement or for color enhancement. We have coatings and inks, film reinforcement, using CNCs as nucleating agents in composites and textiles, in adhesives, paints, agricultural applications, elastomers, water treatment, and oil well completion fluids. And now I've ordered this list here sort of from top to bottom, where the ones at the top are ones that I believe are the least sensitive to the cost of the CNCs themselves, meaning that these are pretty high value applications. Whereas at the bottom of the list, we have very large volume applications that are going to be a little bit more sensitive to the cost of the CNCs. And so we can think about that as we're moving forward, but that there's a lot of importance to developing both these high value and these high volume applications. And then I like to use the analogy of an iceberg, because we have lots of icebergs in Canada, but also to say that I think we're really only at the tip of the iceberg. So not only are there a lot of products coming in the pipeline, there's all sorts of things that we just don't know about yet. And so this is a really exciting time for nanocellulose and for CNCs in particular, really for the products to start hitting the market. But during these scientific advancements and this product development, this has really helped us to understand the challenges better than ever before. And so we know that these challenges are scientific opportunities for us to collaborate and work together. We know that we need more market pull, and that with more market pull and more volume of production, that the costs will come down. And we've also identified that in a lot of applications, cellulose nanocrystals aren't a drop-in solution. And so that's going to take a little bit of work on our part. In 2015, FP Innovations launched a nanocellulose challenge project or program, and so we've all been working in a lot of these areas over the last decade, really looking at ways to improve, for example, compatibilization and dispersion and characterization. And so I was asked to address this question here today: how has increased nanocellulose awareness impacted Canada? And I have 7 ways that this increased awareness has impacted us. And so the first is there are more researchers working in Canada on cellulose nanocrystals. And along with more researchers, we have more government funding, and we have more nanocellulose inventions that are making their way through technology accelerators. Increased awareness of nanocellulose had led us to have more industrial partners. Lots of these partners are in Canada, but most of them are multinational global industries. And you can see they cover a huge range of sectors, and this is really just only a snapshot of them. This has also led to more academic collaborators outside of Canada, at least 50 that I show here, but I'm sure there's even more. And so working up to number 5, how has nanocellulose awareness impacted Canada? It's really helped us to understand the importance of standards development, and Canada's taken a lead role there. So we know that to really move science to technology, that the key is going to be to understand metrology and measurements. And Canada has led this through ISO in Technical Committees 229 in nanotechnology and Technical Committee 6 for pulp and paper. And so we've led a number of efforts, we've given input in others, and we've developed our own standards through the Canadian Standards Association. Okay, number 5 here, we've paved the way with nanocellulose for other renewable nanomaterials, being things like nanolignin and nanochitin. And it's allowed us to start answering the question, where does nanocellulose stand out over other bio-based nanomaterials or pulp or even sawdust, because it's a cellulose particle? And then finally, last but not least, and probably the most important in my role as a professor, is that increased nanocellulose awareness has attracted bright young minds. And so these students and researchers are motivated by sustainability, and they're captivated by nanotechnology, and they're hardworking, creative, and they keep us on our toes. So they've gone on to great careers in industry across many, many sectors, working with startups, working with nanocellulose producers, in patent offices, research institutes around the world, and recently in government. So both national and provincial government, we have students that have gone on to the forestry and agriculture sectors, Environment Canada, Health Canada, Natural Resources Canada, and are working in policy in really important areas there. Okay, and so I think I'll stop there with this photo that I believe truly shows the future and the promise of nanocellulose. Thank you very much.
Thank you very much, Emily. I mean, it's fascinating how research in a country can lead to industrial activities on that scale. So I think, as far as I understand, many of the applications of cellulose nanocrystals are related to rheological properties. If we think in terms of those very particular effects, such as the kinematic behavior, the beautiful colors that you can generate, that would be much more demanding to implement, wouldn't it? What do you think is required to really make use of this particular phenomenon?
Yeah, I mean, you highlight a few good points. It's obviously easy to work with nanocellulose in water and process in water. So those are the applications that we see coming to be products faster. But I think the last 10 years has shown huge advances in using nanocellulose in plastics and elastomers, and also looking at ways to really speed up the drying and the way that we can get these different iridescent colors. I know there are some great spin-off companies that are doing a really good job in terms of roll-to-roll printing and the ability to produce colors, but there are always challenges. It's the invention of new equipment, right? This goes back to it's not a drop-in solution.
No.
So working in water is both a challenge and an advantage from sustainability, but then we spend a lot of time drying, right?
Yeah.
And so I think it's really in the processing equipment and the drying that we have a bit more work to do.
Yeah, but I guess also the specification for those cellulose nanocrystals will be much more narrow, because in order to achieve that, won't it? I mean, you need better control of length aspect ratio.
I think, you know, in our work where we looked at all the different methods, we really considered good cellulose nanocrystals, the ones that would have this optical property as well. So I would say it's not quite as sensitive to production method or dimensions as you think. But yes, of course, we need reproducible materials, and small changes will change how you process and the properties that you get. But I think that the liquid crystal properties are surprisingly robust, actually.
Okay, very good. Thank you. So Akira, I have a question for you as well. I mean, I visited several times and have talked to Japanese companies. I think it's quite impressive from a Western world perspective. I think the patience from Japanese companies and the realization that you need knowledge in order to develop these products. I think that's very impressive. But in the end, there will be the same requirements from nanocellulose products in Japan, so which is cost. Can you and those fibrils that you speak about, which are chemically modified, they obviously carry a higher cost than more simple nanocellulose products. Can you let us know a little bit how Japanese researchers and industry are addressing this problem with cost?
Yes, cost is a very important problem issues. However, to the pulp and paper company, they are trying to change their enterprise from conventional pulp and paper to more, biomass-based biorefinery companies for the materials and both energy, biomass energy. In that case, they have to develop original, unique, and new materials promising for future our living lives for sustainable aspects or like this. So they are not trying to, first they are trying to replace the conventional plastic materials, for example, glass wool containing plastic composite to nanocellulose containing composite. It's a large quantity in the automotive fields, but to replace the already present materials, the price should be lower, or performance should be twice or three times much better. It's quite difficult at this moment, because of the price of CNF is expensive at this moment. However, the original resources, the paper pulp price is around still $1 for dry ton. So if we can increase the quantity of the nanocellulose or chemically modified pulp fibers, the price will go down and down and down. So now at this moment it's a kind of bottom or valley region, so they have to be patient, but still they are making investment for money, time, and human resources
Yes.
to develop new materials. So they are taking a risk, but challenging. Otherwise, they cannot survive at
No.
the present, pulp and paper production situation. So
Yeah.
that is the reason keeping the number of employees, and they are trying to change the enterprise. Like traditionally, the printing companies are now the commercial printing to the electronics, and the Toray, Asahi, Teijin, and Kurare, such viscose rayon companies are changed to the integrated chemical company based on oil.
Yes.
So
Yeah.
they are seriously considering this is a very not so good situation, but it's a chance to survive based on
Yes.
the biomass resources, biorefinery company. So that's the reason. I think it's a cultural difference between
Yes.
European American
Absolutely. Yeah.
companies, yeah, and Japan.
Yeah.
Last time was surprised that to hear that the researchers in working in the Asahi Chemicals, how many years have you working?
Yes.
Or
Yes.
he answered more than 10 years or something.
Yes. Precisely.
Yes.
No, it's very impressive. Yeah.
Yeah.
Thank you
So
very much, Akira,
yeah,
for
sure. My
yes.
pleasure.
Thank you very much, and thank you,
My
Emily.
pleasure.
Thank you very much. So we now move on to the next part of the seminar, and this will be more of an industrial application-oriented perspective. And the first speaker is Sébastien Courbet from CelluForce in Canada, Montreal. He's the CEO, and he will present his company and their products.
Thank you. Good morning or afternoon, everyone. It's a pleasure to join you today for this Wallenberg Prize webinar. I'd like to start by thanking the organizers for including us in a program that celebrates not only scientific excellence, but also the journey of innovation to impact. And that's exactly the path we're on at CelluForce. Now, as many of you know, and as Emily has said, CelluForce is the world's first and still leading producer of cellulose nanocrystals, or CNCs in short. What makes this material unique isn't just its nanoscale structure, its impressive technical properties. It's the intersection it represents between performance and sustainability, and between renewable materials and advanced functionality, and also between fundamental research and commercial reality. Today, I'll share how CelluForce is advancing that journey, how we're scaling production, expanding partnerships, and creating real-world applications for CNCs, what we've learned about bringing a new material to market, and why nanocellulose, once a scientific curiosity, is now on the cusp of becoming a large industrial product. Let's begin with the material itself. Emily spoke about this a bit earlier on today. As you know, cellulose nanocrystals are derived from the most abundant biopolymer on Earth, cellulose, the structural component of plants and trees. And through a controlled process, we extract the crystalline regions of cellulose fibers, resulting in rod-like nanoparticles with impressive properties. We have high stiffness, stronger than steel by weight. We have a very large surface area, ideal for chemical interaction, good heat stability, making the CNCs useful for films, coatings, and composite. But what makes CNCs so compelling is that these properties come from nature, and they're being delivered at industrial scale. Our facility in Windsor, Quebec produces CNCs at metric ton quantities, supporting commercial development globally. The timing is also critical. Today's industries are under intense pressure to decarbonize, reduce waste, or deliver more with less. The materials we've relied on for the past century, fossil-derived polymers, inorganic fillers, fluorochemicals, are being reevaluated. Regulators are acting, consumers are paying more attention. And the winners will be those who can deliver both technical performance and environmental credibility. That's the opportunity we see with CNCs to become not just a better alternative, but a necessary innovation. So at CelluForce, we spent over a decade turning that vision into a reality. We've gone from pilot lines to full-scale manufacturing, from feasibility studies to product launches. And most importantly, we've identified the markets where CNCs don't just fit, where they solve a real problem. Now, let me share 4 areas where our work has been and where it's gaining momentum. So people often think that oil field applications was where we sold our first commercial products. Well, in fact, we started selling product as early as 2017 in rubber goods. For close to 10 years now, our products have been used as a bio-based reinforcing agents in rubber systems. In these formulations, CNCs enhance mechanical properties, modulus, fatigue life, tear strength, while offering a sustainable alternative to traditional fillers. We're now in the midst of a broader market expansion, working closely with formulation partners to make CNCs easier to use. This is always an important point, and make them more accessible and tailored to specific elastomer chemistries, where unlike carbon black or silica, CNCs do not increase density and integrate without the need for complex surface treatments. Oilfield applications became the second commercial market starting in 2018. Since then, CNCs have been extensively used as a rheology modifier in various completion fluids, where they help maintain viscosity under high pressure and temperature. They improve fluid carrying capacity for proppants and solids, and of course, they reduce the environmental impact. Unlike synthetic polymers, CNCs are biodegradable and do not persist in the formation, a growing concern for operators and regulators alike. Our partner, SLB, a global leader in oilfield services, has been on board since day one. We've seen year-on-year growth in product sales, and we're actively working with them to explore new product variations and expanded applications across geographies. Now, one of the fastest growing markets for us today is cosmetics. Since 2020, we've collaborated with multinational beauty and skincare companies to incorporate CNCs as natural bioparticles, primarily as a replacement for microplastics in creams and lotions, requiring sensory performance. CNCs provide a silky, luxurious feel while improving product stability, texture, and film formation on the skin. Importantly, they're marine biodegradable and pose no threat to coral reefs or aquatic ecosystems, an increasing concern in global regulations. In addition, as Emily said, and as you know from Derek Gray's work, CNCs can form structural colors and are now being used for producing glitters that are environmentally friendly. We are proud to be working with SparkCell, a UK-based startup company, to transform Derek's dream into a commercial reality as we speak. And as bans on microbeads and synthetic particulates expand, we're positioned to as a ready-to-scale solution with clean beauty credentials. With multiple new projects in the pipeline, cosmetic is quickly becoming one of our largest and most dynamic markets. And finally, our newest commercial frontier, high barrier food packaging. Our flagship product here is CelluShield, a CNC-based coating that significantly enhances gas barrier in flexible packaging. And the driver here is clear. Brands and converters are under pressure to eliminate PFAS, chlorinated compounds, and multi-layer plastics from food contact materials. CelluShield is a water-based compostable and enables recyclable monomaterial formats without compromising barrier performance. So we're currently working with packaging converters and consumer good companies in North America and in Europe to integrate CelluShield into scalable solutions. Early trials show log-scale improvements in oxygen resistance while achieving good print receptivity, recyclability, and compostability. Now, these are just 4 of the most active sectors we're in. We also see strong potential and actually generate sales in paints and coatings, agricultural products, and even a newer one, medical devices, where one of our partners is, as we speak, conducting very interesting human clinical trials for a CNC-based osteoarthritis injectable treatment to be commercially launched later this year or early in 2026. Now, the key takeaway is this: CNCs are not a niche additive. They're a versatile materials platform capable of solving complex technical challenges across industries. And as CelluForce, we're proving that platform works in the lab, in the field, and in the marketplace. Now, commercialization doesn't happen in isolation. It requires infrastructure, incredible resilience, because it's been a long time, and a relentless focus on customer support. That's why we're now creating the CelluForce Innovation Hub in Canada. Our new facility will co-locate our application development labs with our full suite of characterization tools, the pilot plant, previously owned and operated by FP Innovations, our long-term R&D partner, and our full-scale plant. Now, this ecosystem will allow us to move quickly from concept to prototype to scale up, while giving customers the confidence that we can support them technically and commercially. This goes hand in hand with the development of 3 different types of products to match customer-specific applications requirements, and our foray into nano-integrated products that will speed up time to market. Now, after more than a decade in this space, we've learned a few things that I think are worth sharing. First, materials alone don't win markets, solutions do. Success depends on integration. As Emily said, CNCs is not always a drop-in, so CNCs must fit into the existing formulation and supply chains. That's why we focus so heavily on technical service and application support. Second, not every market moves at the same speed. Sectors like packaging and coatings, where regulation are shifting and sustainability is a commercial driver, move quickly, while others, like construction materials, require long validation cycles, but that doesn't mean we ignore them. We stay engaged, we stay ready to move into these markets. Third, collaboration is everything. We're not here to sell a powder. We're here to co-develop the next generation of products with our customers, and working hand in hand to solve and get across or over challenges is very important. And finally, scale matters. You know, early on there were questions about spending so much money on a large plant, but if you can't produce at commercial volume, you're not in the game. And that's why we continue also to invest in production capacity, supply chain resilience, and quality systems. So where do we go from here? Our goal is to see CNCs become as established and well understood as other performance additives like carbon black, fumed silica, or titanium dioxide. But CNCs, of course, offer something fundamentally different. They're renewable, biodegradable, and in many formulations, functionally superior. It's just a matter of finding the right integration and formulation into these products. Now, the road ahead calls for continued exploration, deeper technical collaborations, broader validation across industries, and ongoing investment in both scale and scientific understanding. You know, we're not finished with the production process and how to best use the material in different applications. So at CelluForce, we believe the material is ready for further growth, and together we believe we can shape the future it enables. Thank you very much.
Interesting, Sebastian. As a composites guy, it was good to see that you're working hard on materials. Thank you very much for your insights. The next speaker is Yoshiharu Matsunaga. He's from NEDO in Japan. So this is the government organization that is helping to implement industrial technology, and part of their job is to support research and its introduction into industry. And this organization has carried out a lot of funding for initiatives in Japan. Among other things, they have funded pilot plants and made them accessible for a large number of companies. Please, Mr. Matsunaga.
Thank you for giving me this opportunity to introduce NEDO and the CNF project. I'd like to express my deep gratitude to Professor Isogai and Mr. Shiba Terabani and Marcus Wallenberg Foundation for inviting me. My name is Matsunaga, and three members are supporting the CNF project at NEDO. About NEDO, NEDO is the National Research and Development Agency that creates innovation by promoting technological environment necessary for realization of sustainable society. As you can see here, NEDO has many departments, and I belong to the biological and material department here. This department manages and supports related projects. CNF project is one of them and is managed by 4 members. NEDO is an innovation accelerator. We promote technology development by carrying out evaluation and allocating funding to the promising project to accelerate the practical application of project result. The total budget and its breakdown are about this. The CNF project will provide support with a budget of 600 to 700 million yen per year over a 5 years period. NEDO reviews a medium-term plan every 5 years. The latest fifth 5 years plan is about this. 1. Creating innovation through research and development management. 2. Fostering technologies based on startup. NEDO provides support through a variety of assistance frameworks. On the left side are the basic technologies, and you go to the right, the technologies are closer to practical application and the production capacity increased. 3. Strengthening and accumulating technology intelligence, like this. From here, I'd like to introduce the CNF project that we are supporting. This project consists of 3 sub-projects. This will lead to remarkably lower cost, innovative manufacturing. And technology application development will lead to product amount remarkably large at various industrial fields. And safety assessment will help convey to manufacturers and customers that the CNF material is safe to use. And now, another project is also running to show the environmental performance of CNF materials quantitatively using a method called life cycle assessment to see if they are truly environmentally friendly or not. This diagram shows the types of products it will be used in and how production volume will increase. And we are continuing developing with this goal in mind. Will this actually become a product in 2025? And now we did it or not? Here, I would like to introduce the innovative manufacturing project along with the photos of the people involved in the development. It's one of them in this project. The Kyoto process is a manufacturing method developed by Professor Yano of Kyoto University, which involves the integrated the process of defibering CNF and kneading it with resin. There are resin pellets containing 30% CNF. It's master batch. The next project, this one of the applied technology project. New user for CNF's interior building materials for housing and other applications. These plates are composed of 100% CNF and have very high stiffness and bending strength. However, building materials are very cost sensitive. As the usage increase, price will fall. So this is an industry sector where application is expected. There are members that evaluate the safety of CNF, write up papers, and publish their findings to the world. The hazards of inhalation exposure are evaluated, but dermal and oral exposure are also being studied. Furthermore, research is being conducted to see whether disposal in the ocean will have a negative impact or not on marine life. Cell tests are main method, but the animal tests are also conducted as necessary. From here, I'd like to introduce some business that have actually succeeded in mass production and announce in a press release that they have installed plant equipment. Their manufacturing method applies the Kyoto process and combines it with paper making technology to create an integrated manufacturing process. Diocese has decided to install a commercial plant for LX67 and will build a facility with an annual production capacity 2,000 tons in fiscal 2025 this year. There are resin pellets containing 67% CNF. It's master batch. When CNF fibers are mixed with resin, the fluidity decreases, and they do not mix well, but they have solved this problem applied by paper making technology, chemical treatment. Another example launched. This belt has been developed by adding CNF to rubber and dispersing it evenly, which increases the belt power transmission efficiency. As a result of successfully development for fuel-efficient large buggies and large scooters, this belt has been sold since this year. Like this, a lot of products are beginning to be launched. There are examples of successful CNS-related technology development. It has high rigidity, but low toughness and prone to cracking. These are still issues to be remained, such as impact resistance. We believe that it will make a big difference when used in automotives about mobilities. I think it's important to continue a project like this until this project is successful. Resistance is power. Keep going until you succeed. Thank you.
Thank you very much, Mr. Matsunaga. We are very impressed by the long-term commitment by the Japanese government. Thank you very much. So we then move on to the next speaker, which is Dr. Hans-Henrik Øvrebø from Børregård in Norway. He's the CTO of the Exilva effort on microfibrillated cellulose.
First of all, thank you for the invitation to this webinar and also the kind introduction from Professor Lars. I met Lars many years ago in connection with a project funded by the EU, the so-called flagship projects in 2020. We had a great collaboration for developing the market and the applications for microfibrillated cellulose or cellulose nanofibrils, regarding what you call it. And in that connection, we had several discussions about how to innovate and the innovation process. And actually, that's the topic for my talk or contribution to this webinar today. So first, a little small background about Borregaard. We are truly a biorefinery. We are utilizing 96% of the wood log, producing a large variety of products. As you could see, it's more than 800 products based on the wood, and we are consuming 1 million square meters of Norway's spruce, and we are truly an international company with businesses in 13 countries and sales to 100 countries. And the sales outside Norway is 90-70%. If you look at this overview of the biorefinery, you will see that the cellulose fibrils or microfibrillated cellulose or cellulose nanofibrils or whatever you call it is sorted under the specialty cellulose. And this project of making cellulose fibrils started long time back in time, where we would like to increase the value generation on the specialty cellulose. And at that time, we decided to try to do something very different from what we had done before. And we had several different projects which were innovating in both the product dimension and in the process dimensions and for new markets. And you see that is increasing the reward of the project, but also the degree of risk, which has been mentioned before. And we realized that the biggest challenge with these projects is to harmonize the different dimensions. You make a product and you adapt the process, and then you need to check off with the market, and then you need to readjust, and then you need to take a decision at a certain point in time about the product and the process to target the market. And as mentioned by Sebastian, it's important then to have sufficient capacity. So you need to have real industrial capacity when you go into the market. And also mentioned before in this seminar, it is truly a long-term strategy. So it must be answered in the top management of your company, and you need to have patent funders. And also mention you need to have an open innovation strategy, meaning that you are collaborating closely with your customers and also with the institutions. The journey for Borregaard to the cellulose fibrils started in 2005. As mentioned, we had more than 10 radical innovation projects, and then we selected 2 of them. And we had a pre-project phase in 2012, the second project phase in 2014, and we decided to build the industrial scale plant, and we started the production at the very end of 2016. And since then, we have been working a lot to develop the market. And what we have noticed is that the challenge of developing the market is in many cases harder than developing the product and the process. The reason is that normally you have full control over your own efforts when you're developing the product and the process. And the process of getting trust and insight and understanding of the applications is a complex process, and it takes time. And we also notice that the efficiency of these technologies are extremely high, so that the number of customers to build up volume is large. For Exilva, the main benefits is that it brings barrier properties and film properties and rheology properties, and it goes into a wide range of applications, ranging actually from construction to agri to personal care. And we see a great demand these days to find technologies that are both sustainable and giving performance. It's not enough to be sustainable. You also need to have the performance. And that's a challenge these days to substitute the well-established technologies with sustainable performing technologies. That was actually what I was thinking to have as an introduction for the later on discussion we can have about the process of innovation within the pulp and paper industry.
I will have a little bit longer discussion with you in the question and answers section. Thank you very much. So then we will move on to the question and answer session with the industrial and government representatives. Very good. So Sebastian, I would like to start with you. I think this concept that Hans Henrik introduced, where he talks about radical innovation, is something that is familiar to you at least in terms of daily experience. So I'm curious. You mentioned in your talk, you said you work more with formulations, and you also said that problem solving is essential. Could you expand a little bit on those statements? What it means?
Sure. I think it goes back to what Hans was saying in terms of making sure we demonstrate performance and we can replace existing products. So working with customers to do trials and errors and integrate the product into the existing formulation is quite challenging. You really need to have a very committed partner to do this. And because the product is also can do several things in several different markets, it becomes very difficult for a company like ours to be specialists in all the sectors. So you need to rely on institutions or customers. And as Anne said as well, you're kind of losing control sometimes on the time to market. And so a lot of our work is about trying to give better tools for the customers to integrate this into their products, to speed up their development work and get this to market faster.
Yeah, but it must be difficult. I think the conditions in Japan are unique. The long-term perspective is different from what we have in the Western world. So how do you address that in your case? It must be difficult.
Yes. Well, as I said, there's a couple of ways to do this. So first, you need to find the right partner, and again, you're talking sometimes between 3 to even 5, 6, 7 years of development, and even the people challenge. People move positions in those large corporations you're working with. So sometimes a project, even though is good, is changing or dropped. So finding the right partners, having a champion in those companies is very important. But as I said, doing some of the pre-work in certain sectors that you want to go after, so that when you're presenting to a customer or working with a customer, you've done part of the integration work, so that project doesn't last as long with the particular customers or partner.
Okay, thank you. Mr. Matsunaga, I had the privilege of visiting one of your activities a couple of years ago, which was very interesting. You invited, well, I think there were several hundreds representatives from different companies. There were as many people from academia, and my impression was that you organized sort of a mingle, that all these players were encouraged to communicate, to send samples. I think you even facilitated so that samples would be readily available. So this is sort of an interesting approach, and I wonder a little bit, how important do you think this activity was for progress in Japan?
Many companies and many universities are tagged with that same theme to practical application. We support the discussion. With discussion chance, we have accelerate, or we have a ceremony to communicate with academia and academic and cooperation.
Very good.
Several times we are to
I think, for instance, that nanocellulose produced in the companies with pilot plants supported by the government, they were distributed to other companies as well. So it seems a very open process.
I can support Matsunaga-san.
Thank
Yes.
you.
Yes, they are supporting but the individual company and the university relationship is very confidential. So they have so many information gathered in NEDO, such like 13 project, and maybe there are some a different deviation of the achievement ratio or like this, but very strong support, because for example the Daewoo and the Kao company and the other companies installed a large scale pilot plant supported by NEDO, and usually in the case of companies 50%, right? 50% support, and 50% they have to pay, taking a risk or something.
Yep. Okay. Thank you very much. So Hans-Henrik, I remember also that in your initial efforts you were supporting the concept of open innovation, trying also in a way to work with customers in this way. Can you let us know a little bit how this worked out?
It's like I mentioned before in this by Sebastian, that you need to have several meetings and build some trust. And for some of the customers, it's possible to have an open innovation so that you could both parties could innovate together and benefit from it and further take further advantages on the learnings. And in other situations, it's more of a bilateral closed innovation where it's a high secrecy.
Yes.
So the best situation is, of course, if you're able to have projects where you can have non-confidential developments, for instance, between the institutes, the partners.
But you also mentioned that you need to work with a large, when it's something like a nanocellulosic product, you need to work with a large number of customers initially. That's what you stated. But at the same time, we now understand that you need deep collaboration with respect to problem solving and working out the specific solution. So this is a little bit of a conflict, isn't it?
Yes, it is. And in the very beginning, we had only a few very large partners, and we quickly realized that to understand more about this material, we needed to offer more samples and be involved more in the market. But again, then we realized, I think also Sebastian mentioned it, you can't be an expert in all fields. So that's a real challenge when you're entering into so many different application areas. How can you then be a good partner and giving insight? And then we realized that we need to focus on the product, the logistics, how to incorporate it. It's not a drop-in solutions. Trying to have a good dialogue, defining what is on their end and what should we and how can we help, and then also involve a third party to make demonstrators to show how it works, to make it more easy to pass the barriers, because this is a novel product with a novel format, and it's not a simple drop-in. So you need to tweak it around and maybe also have a third party helping you.
So your version of nanocellulose is microfibrillated cellulose with sort of native cellulose structure. So when you listen to these this presentation from Japan, for instance, where most of the nanocellulose is highly specialized, carefully controlled surface chemistries, what is the reasoning behind your choice there of approach?
We actually evaluated more options, also doing chemical modification. However, we were early on the sustainability path. So we said that we should make a product that is still cellulose.
Okay.
And that's also for not only for sustainability reasons, it's also for regulatory reasons.
Okay.
It's easier to have a novel product which is, so to say, not novel. It's still cellulose.
Yep.
So our process is water-based, and it delivers cellulose, non-modified cellulose.
So I would like to thank all of you for providing this alternative perspective with respect to applications and the industrial perspective. So thank you very much for your contributions. I guess I could finish off by saying that one learning point with respect to the future is that when you have radical innovation in terms of nanocellulose, it is something that takes time. So in order to reach the market breakthroughs, you need to have a long-term perspective. I think another interesting aspect that Professor Isogai mentioned briefly is that there's a lot of potential in improving pulp and paper products based on our insights on nanocellulose. And this also goes for wood, for multifunctional wood materials, which I think we will see in the future. And with that, I would like to hand over to the Executive Secretary of the Marcus Wallenberg Prize, Dr. Mikael Hamnes.
Thank you for an excellent hosting of the webinar, and be prepared to join me in a moment again, because we have come to the exciting moment of the year when I have the right and the honor to present the 2025 Marcus Wallenberg Prize winner. But before that, I will use a couple of minutes to describe the criteria and the process for winning this award. First, the prize is awarded to recognize, encourage, and stimulate path-breaking scientific achievements, which significantly contribute to broader knowledge and technological development within the broad fields of interest to the forest industry. The prize is awarded to an individual or a smaller group of individuals if the achievement was made by a team. They should have published scientific path-breaking achievements within the field of the forest industry. The scientific achievements shall also have a clear impact potential to how the forest industry sector is acting and developing. So those are the criteria. Then to the process. The board of the Marcus Wallenberg Foundation is deciding about the winner after hearing the selection committee proposal. And the selection committee consists of members with adequate and overall competencies in the broad fields of interest of the sector, forestry sector. But then the selection committee needs nominations to assess. And we have an annual nomination period starting from February throughout April for collecting nominations to the award. These nominations are then duly examined and by the selection committee, and at the end of that process, every year the selection committee identifies and presents their proposal to the board of directors. And that has now happened also for 2025. So now we have the winner of the 2025 Marcus Wallenberg Prize. It is awarded to Dr. Gerald Tuscan for his pioneering work in sequencing and analyzing the first tree genome. His leadership in this project has revolutionized research in tree and forest genomics and biotechnology, paving the way for genome-based breeding of commercially important trees. Dr. Taskan's work has significantly contributed to advanced tree breeding. Genome-based selection of tree varieties with improved properties speeds up the breeding cycle and results in enhanced traits such as improved growth, resistance to diseases, and better wood quality. This allows for more agile adjustments of tree properties. For instance, to increase trees' tolerance to ongoing climate change and resistance to climate-induced pests and pathogens. Genomic-based tree breeding opens new avenues for science and practice to understand the interlinkages between trees and the changing environment, contributing to the foundation for future fit and resilient trees. Isn't that a really super good reason for awarding Dr. Taskan for his achievements? So, Lars, please join me. Emily, please join me, and let's congratulate Dr. Gerald Taskan on behalf of the Marcus Wallenberg Foundation and all the Marcus Wallenberg Prize friends, present and new friends. So, big congratulations, Dr. Taskan.